that's far off in the class, but I just wanted to show how even a kind of simple modification of the linear transport equation can massively change the types of solutions that you get, okay? So that's a sort of drawing a contrast between linearity and nonlinearity, even simple nonlinearity, okay? So, and that really gets into the issue of well-posedness, okay, that we talked about some yesterday. Now, well-posedness is much easier to address, okay, in linear equations than it is in nonlinear equations. So I'm going to start by going through the case of linear transport, okay, as an example of how we kind of build out a description of well-posedness for a PDE, and in particular an initial value problem, okay? So let's say that we have the following PDE, and this is our linear transport equation, again defined on the reals for t greater than 0, okay? IC is our initial condition. This is just going to be u of x equals some unknown function u0 of x, and that needs to be defined on R in order to describe our full range of possible x values, okay? So this is our initial value problem, our IVP, okay? And we know already that our solution is u of x is equal to u0 of x minus ct. We've worked that out already. We know that's one solution. We don't know actually yet if there might be other solutions to our initial value problem, okay? And so the question is, if we want to look at well-posedness, we need to look at 3 different things, okay? Well, let me just enumerate them here, okay? As I said yesterday, or I guess on Monday, existence of solutions is the first condition we need to address in the case of well-posedness, okay? Can I even get a solution to this problem, okay? Uniqueness poses the question, is it the only solution, okay? Breaking this is not necessarily going to destroy your ability to interpret a model, okay? But it's just definitely going to complicate things. The first condition is really the kicker. And then the last condition is what we call continuous dependence, okay? And here we're asking, is it robust to changes in initial conditions, boundary conditions, or parameters, okay? Model parameters, like C in this case would be the speed of the transport equation, okay? So these are our 3 conditions. And what we're going to build up in kind of the first few weeks of the course, even up to a couple months, is methods for checking these things in some canonical PDEs that we'll come across, in addition to just being able to find solutions at all, okay? And so we've already kind of hit on a fast and loose method for finding the solution in our example, okay? And so the answer to question 1 is yes, okay? We have a solution. We don't know if it's the only one, okay? And that solution is u0 of x minus ct, okay? The second question is it unique, okay? And at this point, we're Not sure, okay? We need to know how to check this, okay? And so we'll build up a way of doing this shortly, okay? And the third question, okay, does it depend continuously on initial conditions, okay, parameters of the model? Again, we're not sure, okay? We need a method for checking that, okay? So you can see that existence, as long as you have a method for finding the solution, that's not too hard to check. Uniqueness usually requires a little bit more work, okay? Take a breath. Questions so far? You need to go back to anything? Okay. All right, so let's see how this works, okay? So for uniqueness, we have a lot of tools for doing this that I'll share, okay, as we go throughout the course. And one of them is what's called the energy method, okay? And here we're going to do it for the transport equation, okay? But we're going to do this over and over again for all of our linear PDEs that we come across, okay? And this is the formula for doing that, okay? How do you show that a solution is unique, okay? Well, the energy method says, let's assume that we have two solutions, okay? U and V, and they both solve U sub t plus c ux equals 0, okay? And just for completeness, I'll say, you know, V solves the same equation for V, okay? If we want to show that U and V are the same, can anybody posit a guess of something we might do in order to prove this?
What U minus V solves in this.
Yeah, so U minus V, if you take U minus V, okay, then sometimes it can be easier to show that something is 0 than that something is equal to something else, okay? So as Caleb says, if we take a variable W, maybe there's a way that we can show that W is 0, okay? So in fact, because of linearity, this also solves, okay, Wt plus C Wx equals 0. Great, okay? So what do I have then? I have that 0 is equal to this equation here, okay? And the idea with the energy method usually is that you want to build up a functional. What's a functional? It's just something that you plug a function into and it spits out a scalar value, okay? So usually it's going to involve some function itself of your unknown function, okay? And then you're going to integrate over that, okay? So what I'm going to write down now is a few steps in order to build up this function, whole. It's not immediately obvious where this comes from, except for the fact that you usually want the functional to involve your unknown function or its derivatives squared. Why? Because then if you integrate that, you typically know that the thing that you're integrating is non-negative. So if the integral ends up being 0, you know that the integrand inside actually has to be 0, and it's not just things above and below 0 are canceling each other out. So typically what happens with a functional is that you're going to write something down that involves quadratic or quartic terms of your unknown function or its derivatives, okay? So in order to build this up, okay, we write down the following equation, that 0 is equal to, I dropped my C there. I'm going to just squeeze it in there. W times W sub t, plus CWX, okay? And so if I distribute that, I get WWT plus CWWX, okay? Well, what does that look like? I can use the chain rule to rewrite that as 1/2 W squared differentiated with respect to t plus c over 2 W squared differentiated with respect to x, okay? You're going to see this pattern over and over when we use this energy method. You usually multiply the PDE itself by the unknown function or the derivative of the unknown function, and you just manipulate it like this in order to get these quadratic terms that are showing up here, okay? So what we have then is if we integrate this left-hand side, again, that should be 0. So 0, the integral of 0, okay, from minus infinity to infinity, that's just over the reals, is 0, and that's equal to W xt squared sub t plus CW xt quantity squared sub x, okay, all integrated with respect to x, okay? So we can split this up now into 2 parts, okay? The first of these parts is going to be 1/2 d dt, the integral over r of W squared xt dx. I just pull the differentiation with respect to t out, okay? I have to assume continuity of w, so we have some continuity assumption that's already built in, okay? And if I integrate this next part, right, I can just use fundamental theorem of calculus to write this as c over 2 w squared xt evaluated between minus infinity and infinity, okay? So this term here is going to be equal to 0 as long as w goes to 0, as x goes to positive and negative infinity, okay? So I have 2 assumptions that need satisfying. One is the continuity of w, and the other is that w decays to 0 at positive and negative infinity, okay? So the next part now, okay, is to just take what remains and see that it works out that this implies that w is going to be 0, okay? So what we end up with is d dt now of this integrand, okay, is equal to 0, okay? This implies, okay, that the integral of w squared integrated over dx, okay, is just equal to some constant now, okay? But we know that since the initial conditions imply that w of x0 is equal to u of x0 minus v of x0, and this is equivalent to 0, okay? So the only constant this could possibly equal to is 0, okay? Because it has to be satisfied at t equals 0, okay? So this implies then that capital C, that's probably not the best constant value to use. I'm going to put these little capital marks on it. That C is equivalent to 0. Okay. So as long as W of xt, okay, is continuous, this implies that W is equivalent to 0. Okay. Why do I have to add in that caveat of continuity? Well, because you could always integrate, some function that's 0 everywhere, except for little holes that it has poked in it, where you take on values that are non-zero. Okay, so in order to, preclude these sort of pointwise discontinuities from happening, we have to make an assumption about continuity of W in this case. Okay, so as long as W is bounded, it's continuous, and it tends to 0 as x goes to infinity, then this implies that U is equal to V, or equivalent to V. Okay? Questions about that?
So are we able to interpret this using weak derivatives? And then instead of saying, well, I guess what is the analogous condition to continuity in that case, if we start with like a discontinuous initial condition?
If you have a discontinuous initial condition, you can basically prove uniqueness up to the discontinuity points. So if you have some, jump discontinuity or something like that, your solution's not going to be well behaved there anyway. So you can sort of chop the problem up into the regions around the discontinuity. So you can get away with it, but the results are not going to be as clean as they are in this case. It's a good question, yeah.
Our other assumption that W goes to 0 as x goes to infinities, is that one motivated more by U and V? I guess, how do we assume that one? Or like, what do we just have to?
Yeah, I mean, because otherwise you can't evaluate this limit. So, I mean, usually you're going to get the most definitive results on bounded domains. So unbounded domains always have this, minor issue where you can use an unbounded domain, but things are going to get difficult to prove. If you have a solution that blows up or takes on a non-zero value as you go out to infinity. So usually when you construct a problem, you're going to have a solution and initial conditions that tend to 0 out at infinity. Yeah. Okay. All right. So that's uniqueness. Of course, there's other ways to prove uniqueness, but that's one that we'll come back to a lot.